Hi, in the last video, I discussed about one-way ANOVA, that is also called one-factor analysis of variance, okay? So what we did there is we were comparing the population mean of more than two groups, okay? Because if there are just two group or if there is only one group and then if we are testing the mean of the population or the average value of a population, then you use the t-test, right? But if there are more than two groups, then you use ANOVA, which is in short called analysis of variance, right? So basically I did one example on how to compare the means of more than two groups. And also on the last video, I discussed about the assumptions of one-way ANOVA, right? So there were several assumptions, but two of them are you use R or you use some analysis on those two of those assumptions. One assumption was test of normality, meaning that the variables or the groups must be normally distributed, and then another test was the homogeneity of variance, meaning that the variance on the variables must be equal, or the variance between the groups must be equal, right? For the homogeneity of variance, I actually used several methods there, but I'm going to discuss how to test the homogeneity of variance if there are more than two groups. Okay, so the first test that I'm going to discuss here is the Barlett Test. So Barlett's test is basically the extension of the comparing two variances into multiple variances. Okay, so many methods are used to compare the variances, but Barlett's test is most frequently used, and I will show you Barlett's test and Levine's test with how to do that manually with example. Okay, so this method uses the test statistic as b equals to ln, natural log of the variance, pool variance, right? Natural log of the pool variance we denote by the p square, and sum of ni minus 1, which is same as the total number of the data points in all groups minus the number of categories or number of groups, okay, and minus summation of ni minus 1 times ln si square, where Si square is the group variance, group sample variance. So for each group, you find out the sample variance and you take the natural log, you multiply by the degrees of freedom of that. That means Ni minus 1, okay? And you add that, all those for all of those group. And then here Ni minus 1 is again the sample size minus 1 for each of those samples. So this is the formula for the pool variance, which is S square P, which is the variance, pool variance, is equals to summation of Ni minus 1 times Si square. What does that mean? That means N1 minus 1 times S1 square plus N2 minus 1 times S2 square plus N3 minus 1 times S3 square plus so and so on, okay? And divided by N minus K, all right? So also, so the modified value of the test statistic. Instead of this, people also use the this test statistics we denote by B sub C, which is B over C, where B is that same B, and then C is given by 1 plus 1 over 3k minus 1 summation 1 over n minus 1 minus 1 over summation n minus 1, which is same as total number of, this is same as that value, right? So the total number of data points minus the number of groups or number of columns, okay? Where k is the number of samples, that is the number of groups or number of columns. And for the critical value, we use chi-square right tilt. Or if you want to find out the p value, you can use p chi-square and for the right test, which k minus 1 degrees of freedom. So let us see one example, okay? And then I will show you how to do that by hand manually, and then I will show you how to use R directly, okay? So here, for alpha equals to 0.05, test if the following samples have their population variance equal. So you want to know, these are the samples data, right? So you want to test if the population variance of these three samples are same or not. Or if you can think this way too, if these three samples are taken from the same population, because the same population have the only one variance, right? So so you can think that way too. Okay, so what is the null hypothesis? Is all three variances are equal, population variance, and the alternative is not all variances are equal. So we need to find out first B, and then we'll find out C, and then we will find out BC, that is B over C. So that's what we want to find out. So what I did here is actually I copied that data set. Okay, so you can see here x1 is I need to start with C, right, because there are more than one data points. So x1 is a C, and then 34 I copied that, x2 x3 I copied that. So I need to find out the variance of x1 x2 x3. Why is that? Because you see that I need to find out SI square, that is the variance. SI is the standard deviation of the ith sample. SI square is the variance of the ith sample. Okay, so you need to find out S1 square, S2 square, S3 square, which is variance of the first group, variance of the second group, variance of the third group. That's what these three things are doing. And I need to find out N1, N2, N3, because see, this is N1, N2, N3, N4 like that, right? So I need to find out that N1 is the number of data points on the first sample, N2 is the number of data points in the second sample, and N3 is the number of data points in the third sample. Okay, so K is the number of groups. So that are 1, 2, 3 samples, number of sample or number of groups. So K is 3. So N, the uppercase N, is the total number of data points, including all the samples together. Okay, so that will be N1 plus N2 plus N3, that is 5 plus 5 plus 5, 15. Okay, now how do I find out the pool variance? Pool variance is summation of Ni minus 1 times Si square, that is N1 minus 1 times V1, variance 1, that is S1 square, plus N2 minus 1 times V2 plus N3 minus 1 times V3 divided by N minus K. That's what I did here. Okay, so that is the pool variance. And to find out B, what do? Is B is log of pool variance times summation of, so log of pool variance times this whole summation is N minus K, because it is like N1 minus 1 plus N2 minus 1 plus N3 minus 1 like that. So that is same as N minus K. So times N minus K minus this thing is after that parenthesis. So N1 minus 1 times natural log of S1 square, natural log of variance 1, plus N2 minus 1 times natural log of variance 2, plus N3 minus 1 times natural log of variance 3. That's what I did for B. Okay, and what is C? C is 1 plus 1 over 3 times K minus 1 times, inside the parenthesis there is 1 over N1 minus 1 plus 1 over N2 minus 1 plus N over N3 minus 1. That's what this is, right? And minus 1 over this whole summation is N minus K, because this is like N1 minus 1 plus N2 minus 1 plus N3 minus 1 and so on. So N1 plus N2 plus N3 is capital N, uppercase N, and then minus 1 minus 1 minus 1 will be 3. That is K. So 1 minus 1 over N minus K. Let me run from the beginning. So and then I will list the data what I get there. Okay. So that is N, and then pool variance is there, and B is there, C is there. Now test value, let us look at there. K is 3, N1, N2, N3, they are all 5. Capital N, that is uppercase N, is the total number of data points in the 3 samples, that is 15. S square P is 1.1. How did I get that? That is the pool variance, right? If I run this, that will be 1.1, right? So this pool variance is 1.1. What is C? C is, I can just run this, that C is 1.11. C is 1.11. What is B? B is the right side of that. I copied that and then run that one. That is 0.8063. That's why I did 0.81. What is BC? BC is test value, right? Test value is B over C. Let me run that one. So test value, and then I have a test value. So that is 0.7257. That is the test value. Now, what we need to find out is we need to find out the chi-square value, the p-value, right? So this is taken as the right tail chi-square test. So using the chi-square table with degrees of freedom is 3 minus 1, that is 2, and the right area is alpha equals 0.05. So the p-value is 1 minus p chi-sq, right? So 1 minus p chi-sq, BC is the test value, comma, K minus 1. So that's what I did here on line 206. That's what you got. P is 0.6956. 0.6956. So this p value is greater than alpha, because our alpha was 0.05, right? So the p value is greater than alpha, meaning we do not reject the null hypothesis. So we do not reject the null hypothesis, means we are supporting the null hypothesis, right? That means the variance of these three samples, the population variance of these 3 samples are equal to each other. Okay, so this is what I did manually. But how do I do it directly? So it is similar, very much similar to the one-way ANOVA. First of all, we need to arrange the data into 2 columns. All the x1, x2, x3 into a single column. And then for the first x1, you type just x1, x1, x1 like that. Okay, or you can say whatever name you want to give. Okay, so I want to give you x1 is the first group, x2 is the second group, and x3 is the third group. Let us do that. Okay, x1, x2, x3, and I'm giving. So let me do that. So what I'm doing here is I am writing how many numbers are there in x1. There are 5. So I'm writing x1 5 times, and then x2 5 times, and x3 5 times. These are x1, 5 of them are x1, 5 of them are x2, and 5 of them are x3. And then another is I am writing these values into a single column. First of all, I want to combine them. So p content, I'm just doing these 5 are from the first x1, these 5 are from the second, that is x2, and then these 5 are from the x3. Okay, now I'm writing in terms of the columns. Look at this. If you write in terms of the column, this is similar format we used in one way another, right? So these 5 are from x1, another 5 are from x2, and then another 5 are from x3. Okay, so and then what you do is after you arrange the data into 2 columns, with the first column is only the data, and second column are the groups of those data. When you do that, you just do, after you do that, you do Barlett.test. That's what you do, and we have done in the one way another too. So Barlett.test, p content is the data point, and then wiggle sign, and then the tech is the second column. Okay, second column is the grouping, name of the groups. If you do that, this is what you do. So so line 216, you got p value is 0.6957. that is the exact same p value that we got by using manually. Okay, so this is what you do the Barlett's test using manually or using R directly. If you use R, you need to first arrange the data into 2 columns, with the first column as just the data and the second column as the name of the groups for those data. Okay, and then you just do the Barlett.test. Okay, so p content and wiggle and then tech. That's what you do. So you don't have to do line 214 and line 215 for the Barlett test. Once you define tech and then p content, that is okay. You can do that way. Okay, because it is not using it is using that. You can do that way, or you can use here. What I'm doing here is p content, comma, wiggle and then tech. But which one is data? Data is p data 2. That's what we have. Data is the p data 2. So when you define the data in that way, you don't need the $sign for p content and tech. Okay, guys. So this was the Barlett test. Now, next one is the Levines test. Okay, well, how do you do the Levines test? Let us discuss about that briefly. Again, this is the alternative method for the homogeneity of variance, meaning that which is one of the major requirement for the analysis of variance when we compare the means or the average of more than 2 samples. Okay, now to use the Levines test, we first find the absolute value of the deviations of data from each column to their corresponding column means. So first of all, what you need to do is you need to find out the deviations of the column data from their column means, meaning that you need to subtract each of the data from a column to its column means, and then if there is a negative sign, you ignore that. That's the absolute value thing, right? We first find the absolute value of the deviations from the data from each column to their corresponding column means, that is denoted by GC, that is column means. G1 will be mean of the first column, G2 will be mean of the second column, G3 will be mean of the third column, and so on. And to find out the mean of each column GC, then find out the mean of each column GC, and then mean of overall data. So we need to find out the mean of the overall data also, because we will need to find out the mean of each column GC already in first step. Then find SSC, sum of the square of the deviations of column mean from grand mean, multiply by the number of data in the column, and then also SSC, sum of the square of the deviations of the data from each column to their corresponding column. So this is similar to the one way ANOVA when we did by hand. Okay, and I'll go over each of the steps there later. And the test statistic is given by n minus k. N is the total number of data points, k is the number of groups, and SSC is that thing, we will discuss that. And then over k minus 1 is k is the number of groups, SSC is given by this step. Okay, then find the p-value. How do I find the p-value? We will use the right tail f test again. So since it is right tail, we are doing 1 minus pf, and w is the test value, and then k minus 1 and minus k are the degrees of freedom. And we reject H0 if p is less than alpha. So these are the steps similar to the one way ANOVA, but I'm going to do how to do that exactly, okay, but manually, and then I will show you how to do by R directly as well. Okay, so the example here is the test the homogeneity of variance for the above 3 samples problem. This is exactly the same sample I am picking. I want to test the homogeneity of variance by using the Levines test. I will discuss why Levines test and then why Barlett test, in which condition Levines test is better. So I will discuss about that later, but for now let us do this example. So for the Levines test, you see that this x1 is the exactly the same data. I have x1, x2, x3 exactly the same data from the previous example. So what I am doing here is I can write the, I can write the data dot frame and then see how it looks like. These are the data points, right? So how do I find out? How do I find out first? It says that we need to find out the absolute value of the deviations from the data from each column to their corresponding columns. So what do you need to do? You need to find out the mean of x1, mean of x2, and mean of x3. Okay, and then what you need to do, you can do mean of x1. What will be the mean of x1? Mean of x1 will be 34.6. Similarly, find out mean of x2 and mean of x3. And what you need to do is you need to subtract each of these data from this column mean. Okay, and then if you get negative sign, you ignore that. So we use absolute value. So what you need to do is you need to do absolute value of x1 minus mean of x1, right? Mean of x1. Look at this. This is what you will find out, and then you will get these values there. Okay, so you are subtracting each of these data points from the mean of these values. That's what you get. 0.6, 1.4, 0.6, 0.4, 0.6. Look at this. I denoted that by G1. Similarly, you do for x2, you denote by G2. Similarly, do for x3 and denote by G3. This is the first step. So we found the absolute value of the deviations of the column data from their column means. That's what we do. And this is what I wrote. We here x1 is 34.6. This is the mean of that. X2 is mean of the x2 bar, and x3 bar is mean of x3. Okay, so I use GC equals to XC, the column of x, first x1, x2, x3 minus their column mean. That's what I did, GC. And these are the GC, G1, G2, G3. That's the GC I denote by C is the column. Okay. Also now you need to find out what? After you do that, find out the column means of this, column means of that, column means of that. G1 bar is the column mean of that. G2 bar is the column mean of this column, and G3 bar is column mean of that column. Okay. And then what is the overall mean? Overall mean is the mean of all these data, mean of all these data points. Okay. All together you got G bar equals to 0.83. Let us do that. So G1, I did absolute value of x1 minus mean of x1. G2, G3, I did that. And then I put that one, I put the data dot frame G1, G2, G3. So I put them in the column format. This is what I got. Okay, now, so we need to use this, we need to find out SSC, right? How do I find out SSC? Sum of the square of the deviations of the column mean. Meaning, we need to find out G1 bar minus G bar square plus G2 bar minus G bar square plus G3 bar minus G bar square. That's what it is saying. The sum of square of the deviation of the column mean from grand mean multiplied by the number of data in the column. That is N1, N2, N3, right? So let us see that. So I found N1, N2, N3 there. K is 3, N is the sum of the number of data in each of those. And then I wrote G equals to C. I'm just combining G1, G2, and G3 all together to find out the mean. And then I found X bar equals to mean of G. This is what I found. Now SSC is sum of N1 times mean of this minus mean of overall square. See, mean of G1 minus X bar square plus N2 times mean of G2 minus X bar square, because I denoted by mean of G as X bar. You could write G bar, not a problem. And plus N3 times mean of G3 times minus X bar square. That's what I did. That is SSC. Similarly, what is SSE? SSE is similar. It is error sum of square type of thing, right? What you need to do is you need to do this minus the column mean square plus this minus the column mean square plus this minus 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 column mean square. Look at this. 0.6 minus 0.72. What is the 0.72? Is the column mean of that. and then plus 1.4 minus 0.72 square, and continue doing that up to here. Next, 0.6 minus the column mean of that will be 0.72 again square, plus 0.4 minus 0.72 square, plus and so on. And finally do for this 1.8 minus 1.04 square, because that is the column mean, and continue to that. The final one will be 0.2 minus 1.04 square. If you do that, you will get 2.604 SSE, and SSE will be 0.34. So also n is the total number of data points is 15, k is 3. Thus the test value W is n minus k SSC. This is the same as this one, right? I use that, I got 0.7853. That is the test value or the test statistic. Now to find out the p-value, you do right tail f test. This should be pf, okay, not pm. I'm sorry about that. This should be pf. Okay, that should be pf. And then w, k minus 1, n minus k. That will give you 0.4781. And we get do not reject the null hypothesis. Let me do that. So I got SSC and SSC already. So the w will be n minus k times SSC divided by n k minus 1 times SSC. The whole thing is inside the parentheses, so we are good. So you see that the w value is 0.7852761. That is 0.7853. That's what you got the w value, right? Because when you run that w and then if you do that, you get 0.7852. That is the w value. Now for the p value, you do 1 minus pf and then w, k minus 1, n minus k. If you do that, you get the p value is 0.4781. 0.4781. So this is how, so we found the p-value which is greater than alpha, so we do not reject the null hypothesis, meaning that from either method, so the population variance of those samples are equal because we are not rejecting the null hypothesis. Now, how do you do the Levine's test directly using R? That is the thing. So similar to the previous one, you need to first arrange the data, okay? When you do that, this is the arrangement of the data. First column is all the data. Second column is basically you are writing which group is that. I'm just writing take 1, take 2, take 3. So the first one is these 5 data are from first group. Next 5 data is from second group, and so on. Okay. Now to do the Levene test, you need library call. You need to call the library there. Okay, and then do Levene test p content. That is the p content, and tech. I just name as tech, and the data is p data 2. That is the name of the p data 2, right? And center is mean again. So one of the another advantage of the Levine's test is you can, so what we did is we were taking the mean of these here, right? We are taking the deviations of this data from their mean, but you can take median and take the deviation as in this process and that process too. So I am taking the mean as the center. You could take median as the center as well, okay? And if you run that, you get exactly I'm sorry, I need to run the library, and if you do that, you get the you see that the test value is 0.7853. That's what we got here, and the p value is 0.4781. So we do not reject the null hypothesis. This is how we test the homogeneity of variance by manually and by using R. Okay, guys. So the last slide for the homogeneity of variance is, let us talk about some of the notes on that. Note number 1 is the Barlett test is powerful if the sample populations are normal, but very badly affected by non-normal populations. So the population must be normal. We know how to check the normality, right? If k equals to 2, the Barlett test is equivalent to the variance ratio test. We did that in, I think it was in the 2-sample test, discussing 2-sample test. Next is the Levine's test is an alternative to the Barlett test. The Levine's test is less sensitive than the Barlett test to the departure of normality. So if the data is slightly deviated from the normality, then it is advised to use the Levine's test. Okay. If you have a strong evidence that your data do in fact come from a normal or near normal population distribution, then Barlett's test has better performance. Generally, it is not recommended to test the homogeneity of variance for comparisons of means because ANOVA is robust when even if the variants are slightly different. So usually people don't do the variance test or don't check the homogeneity of variance. Usually they don't do that because the one-way ANOVA or two-way ANOVA, they are strong enough to produce the valid result even if the population is slightly deviated from normality. Okay, guys. So I will post this homework problem in the in the separate sheet. So that is how we do the homogeneity of variance by two different methods, manually and using R. Okay guys, thank you very much.